Welcome to this session on building your own robots at home. My name's Dr. Footleg, and today I'm going to be showing you how you can build robots for Raspberry Pis or Microbits using kits that you can get for relatively low cost and take your coding to a mobile platform in the form of a robot. So what do we mean by a robot in this sense? I'm classing it as anything that enables you to make things move with your code. So we're going to start off with the simple basics of one of the kits which I began with. And if I just swap my view to my desk camera, then you can see here a kit which is the CamJam EduKit 3, and it's a robot that you actually build out of the box it comes in. So it has 2 electric motors with wheels attached and a caster wheel on the front. And inside the box, you get the electronics to plug onto a Raspberry Pi. But before we get the Raspberry Pi involved, I thought it was worth looking at how a motor actually works. A motor is a simple electrical component which converts electricity into motion by rotating. So I've got a motor here with wheels on. I've got a battery pack. If I turn on the power and then just connect the wires, we should see that the motor turns. And if I swap the wires over, so I'm connecting the black to the red and the red to the black, then the motor still works, but it rotates the opposite direction. So I can make a motor rotate in either direction just by changing the way round that we connect the power, the battery in this case. So with that basic principle, we can see how we could make motors drive this box around. The secret to making a robot is how do you actually do that from code? So we're going to look to start with at a simple circuit that enables us to do that without having to connect and disconnect the wires. So you should now be able to see my my presentation, I hope. And we're going to look at very, very simple circuits for driving motors. So starting off with what I just showed you on my desk. This is a battery, a motor represented by this circle with an N in it, and a simple switch. Whilst the switch is off, the motor is not got any power. If we close the switch, then now power flows through the circuit. We traditionally show it flowing from the plus end of the battery around the circuit through the motor turns, and the circuit's completed back to the battery. So we've got a simple circuit, as I showed you, that runs a motor in one direction, but we want to rotate our motor in both directions, and we don't want to have to disconnect and reconnect wires to do so. And the type of circuit which enables us to do that uses 4 switches, and the motor is in the middle of what we would see as an H shape. And it's called an H bridge for this reason. So the 4 switches kind of make up the shape of a letter H, and the bridge or the middle of the H has got the motor on. Now, if we close 2 of the switches as follows, you can see how we've made again our simple circuit. The power's flowing from the battery around the circuit through the motor. The motor rotates clockwise in this case. The circuit's complete. If we open those switches and close the other 2 switches, now you can see that the power is directed through the motor in the opposite direction. So without having to change any of the wiring, we have got a circuit which lets us alter the direction our motor turns. And that's the basic component that you'll find in all of these robot kits. So if we go back to the robot we've got here, in this particular kit, as well as getting a few sensors for detecting things like lines, black and white, so that you can write line following, you get a circuit board which plugs onto the Raspberry Pi. Now, the Raspberry Pi computer has a whole set of input-output pins. And for those of you familiar with Microbit, that's the same. It has a whole set of pins which you can connect up additional electronics to. The problem with these pins is, although they can output power in the form of a signal connected to the plus end of the battery or to the minus end of the battery, if you like, what we would call 0 or 1, or on or off, true or false. So all this terminology is used in coding. The problem is that none of these computer devices can put out the sort of power that a motor needs, and it would actually damage them to connect a motor directly to them. So these motor add-on circuits actually deal with that problem for us. They provide us with the H-bridge circuitry, but also the power management. So they typically have a connector in to put the battery to, and then 2 connectors for the 2 motors, and that enables us to drive a robot. You can get H-bridge circuits like this that plug onto a Raspberry Pi that comes in this CamJam kit. But you can also get H-bridges which plug onto the Microbit. Here's a very similar looking robot, but this one was actually built out of a different cardboard box, and the motors in this case we've bolted onto the box. It's been decorated. This is the Kitty Corn, which was built by some of the girls in my primary school coding club that I host. And the real difference is that the H-bridge board, which we're using here, has a microbit on it. That enables the battery power to be fed in. The battery powers the microbit as well as powering the motors, and it safely directs that power to the motors and gives us the ability to turn the motors in either direction. So let's have a look at the code. Just get my screen share back up. So for those of you familiar with Microbit, you'll know the MakeCode editor. You just go to the website makecode.microbit.org, and you don't need to install any other software. And because the code to control the motor board is a little bit more complicated than your average Microbit project, I actually start with what I call my robot starter project. And what I've done there is I've defined a set of functions which control the power to that H-bridge. And it uses these analog and digital write blocks to set the appropriate pins to turn the motor on. So the motor is getting power either on one direction or the other direction through the H-bridge. So the forwards block sets both motors so the robot drives forwards. The backwards block sets them the opposite way around to go backwards. We've also got the additional ability to set the power being how fast the motor turns. So these H-bridges also enable you in code to control how fast your robot drives the motors. And then we've got blocks for going forward and left at the same time, or to actually turn left and right on the spot. So we can now use those blocks to write some rather neat programs. And I'm going to show you one that's pre-written so that we don't spend too much time doing code. The microbits have a really neat feature that they can send radio messages to each other between one microbit and another. So what we've done here is we've set a radio group. I've set this one to radio group 8. And because once your microbit's programmed, it's not always easy to see, to remember which channel it's on. I also flash that channel up on the microbit when it starts. And then the rest of the code is on the button. So here you can see on button A, I've put some basic code to go forwards for 2 seconds, turn right for 2 seconds, pause for 2 seconds, turn left for 2 seconds, go backwards for 2 seconds. And finally, really important, you need a stop block. Otherwise, you've told your motors to drive, they'll just keep driving and your robot will run off the table. So let's turn that on and see if that code works, first of all. So you see it flashed up number 8 on the camera. And if I press button A, hopefully, if I've got enough room on my desk. So my robot runs forwards for 2 seconds, backwards for 2 seconds. And then it tries to turn round on the spot. So following the code which I've written. So that's how simple it is to build a basic robot. But of course, the real fun comes from radio control. So we've also put in a radio received block here. And we've said that if I receive the string forwards, then call the forwards block. If I receive the string stop, then call the stop block. If I receive the string backwards, call the backwards block, turn left and turn right. So I've also got the ability to make my robot drive from another microbit. So let's have a look at the project that we wrote to transmit messages. So this program goes on a second microbit, and I've kept this one really simple. We need to set the radio group again so that we're on the same channel, so these 2 microbits are talking to each other. And I flash up that number just to show which number it's on when you power it up. And then we've got, if button A is pressed, go forwards. If button B is pressed, go backwards. If buttons A and B are pressed together, then stop. And then I also tried to get a bit clever and said, if I tilt the microbit left whilst button A is pressed, then turn left. And if I tilt it right, then turn right. So that code we've put on this second microbit. So if you look at the camera again, you should be able to see that if I press A, off my robot shoots. And notice it keeps going until I give it another instruction. So I'm going to tell it to go backwards. And now it's going backwards. And if I press both buttons at once, then I can stop it. So in just those few lines of code, we've built a remote controlled microbit robot. Now, you can use exactly the same principles to build all sorts of robots. I'm going to show you another example on the screen now of a kit robot. And this one is actually a kit called the Tiny Four-Wheel Drive. So it has 4 wheels with 4 motors. But if you look carefully at the wiring, the motors are actually wired up in 2 pairs. So the left-hand motors always drive together. The right-hand motors always drive together. And this gives us a much more powerful, speedy robot. And on top, instead of using the Raspberry Pi, which came, electronics that came with this particular kit, I've put one of these micro. This board, by the way, is from Kittronic. I'll show you some links to where you can find all of these kits at the end of the talk. But it just gives you an idea of how you can build something that's a little bit more of a step up from the kind of cardboard box robot. And now we've got 4-wheel drive. This tends to be able to cope with more terrain. It will drive over bumps and things better. And it's a lot of fun. I'm going to show you next a very simple Raspberry Pi robot kit. I'll just put those aside. This kit is called the STS Pi kit, and it's a favorite of mine because it enables you to get started with all sorts of electronics as well as just the robot. So you can see that it's really a Raspberry Pi with a pair of motors, 2 wheels, a caster wheel. So pretty much the same as we saw with the microbit robot, exactly the same principles. And then on top of the Raspberry Pi, I'm using the Explorer Hat Pro. which is a motor driving hat that also provides lots of inputs and outputs for adding additional electronics. And it has a little area for building circuits with the push fit breadboard on top. So we put that onto the Raspberry Pi, and we're connecting to the two motors. And I'm using one of these USB batteries on the back. So if I plug that in and power it on, then that's now booting up. Now, one of the challenges with building a robot is that your Raspberry Pi normally is connected to a screen and has a keyboard and mouse attached. But we want something that's completely mobile. We don't want all of those wires tying it down. We solved the power problem by using a battery pack that's built in, but we need to remotely connect to it. Now, the Raspberry Pi, thankfully, has built into it the VNC, Real VNC software. And you can run Real VNC on a laptop. I'm just trying to get it onto the right screen so that I can show you what I'm looking at. So on my screen now, you should be able to see the VNC viewer that is looking at my Raspberry Pi desktop. Which I've just hit the wrong button and cancel. Just let me share that again. Okay, so you should now be able to see the Raspberry Pi desktop. And this is actually the Raspberry Pi running on the robot. So I've now got complete remote control. My laptop is my screen, my keyboard, my mouse. And I'm going to show you how you can start coding this robot, first of all, using Scratch. So I'm using Scratch 3, which is the latest version, and I've downloaded the desktop version onto the Raspberry Pi because the desktop version of Scratch has built in the ability to talk to hardware that's attached to the Raspberry Pi. So this is going to load up a Scratch blank project to start with. Whilst that's loading, we need to know which connections on the Raspberry Pi are actually used by this Raspberry Pi add-on. And the answer to that is found by looking at a website called Raspberry Pi GPIO Pinout. You go to pinout.xyz. Now this shows you the 40-pin connector on the Raspberry Pi, and it tells you what all of those pins are called and what they do. But you can also search through for pretty much any add-on that's available on the market. And I'm using the a add-on called the Explorer Hat Pro from the company Pimoroni. So I'm going to select Pimoroni, and then I can scroll down, and there it is, the Explorer Hat Pro. So now that I've selected that, you can see that it's highlighted on the pinout diagram all of the pins that are used by the Explorer Hat Pro. And you'll notice that some of them are labeled motor. So there's motor 1 plus, motor 1 minus, motor 2 plus, and motor 2 minus. So they're on, so motor 1 is on the pin BCM19 and BCM20. So if I put power to one or other of those pins, that's going to send that signal to the 8 bridge. So if I switch back to the Raspberry Pi, there's an add-on extension button in Scratch 3 in the desktop edition. And one of the extensions is the Raspberry Pi GPIO lines. And if I select that, then I get these extra blocks where I can ask if a GPIO pin is high or low, meaning powered on or powered off. But I can also set them to high or low. And to control the motor, all I need to do is set the appropriate pins. So I've written a project ready for this so that we don't have to wait while I write all the code. But the principle is very similar to what we did with the Microbit code editor. So I've defined some custom blocks. I've defined a stop block where I set all of those pins to low, meaning off. That will stop the robot, stop the motors. I've defined a forwards block where I've set pin 19 low and pin 26 low, but I've set pin 20 and pin 21 to high. And if you remember, on the Pinout, pin 19 and 20 were the two pins for the motor 1. So if I set one of them high and one of them low, that will send power through the H bridge in one direction. If I set the other one high and the opposite one low, it will send the power through the H bridge the opposite way and make that motor turn in the opposite direction. So 19 and 20 were motor 1. And in the Scratch project, it's 19 I'm setting low and 20 I'm setting high. And likewise for 21 and 26. So then, having got those blocks, I've written a forwards, a backwards, a turn left and a turn right. So to go forwards, I make both motors turn in the same direction. You can see on the camera. To make it backwards, I make them both turn in the same direction, but going the opposite way. To make it turn on the spot, I make one motor go forwards and one motor go backwards. And that causes the motor to spin around. So with that little example program here, I've said, when I click, go forwards, wait a second, go backwards, wait another second, turn left, wait a second, turn right, wait a second, and most important, stop. Because when I say to the motor go forwards, the motor is going to keep going forwards until some other instruction is sent. So this wait 1 second is not telling the robot to wait for 1 second. It's telling the program to wait for 1 second before it gives another instruction to the robot. So we should, if I've got this right, see the robot go forwards for a second, then backwards for a second, then turn left for a second, and then turn right for a second. So let's give it a go. There we go. I'll do that again in case you missed it on the camera. And so now, of course, I can start to write any code I want. So if I wanted to go forwards for 2 seconds, and then I wanted it to turn left, and I could, in fact, rather than duplicating that code, why don't we use a control loop and say repeat 4 times. And I'm going to actually just bring these down to 0.5 seconds so that I don't run off the table. And because I'm not sure quite how far the robot will turn in 1 second, I'm going to, I think 1 second took it slightly less than, let's go for 1.2 seconds. And I'm going to say do that 4 times. And then most important, don't forget to tell it to stop at the end. Otherwise your robot will just keep driving off into the sunset. So let's give that a go. So forwards. So I'm going to do that again because it was very quick and it ran off the table the first time. Forwards for a second, turn left. Now it's doing a complete 180 actually. So my turn left time is probably a little bit too long. Let's try 0.6 and try it again. So my robot's sort of driving in a square, and I now need to work out the timings to get it perfectly to do my 90-degree turn rather than not quite a 90-degree turn. So very quickly, with some very simple code, we've learned how to kind of code our robot. The actual code libraries for a lot of the Raspberry Pi add-ons are written in Python. And so although we've gone straight to the Raspberry Pi pins to drive this particular hat, you can't do that with all of the hats. And you probably want to move on from scratch once you've learned the basics of coding there and explore Python. A tool which I really like is one called Edublox. And the Edublox environment gives you a block-like coding experience like you get in Scratch, but it writes Python code underneath the hood. And very conveniently, it supports the complete capabilities of the Explorer Hat Pro. So I'm going to select Python 3 and Edublox has been upgraded since I last ran it. So they've moved the this is the one bit of my demo I didn't practice. They've moved the Pimoroni features. I wonder if I need to import the library. So the perils of updating your Raspberry Pi just before a demo and not checking that it works. Okay, I'm going to skip over Edublox because it's not actually. I'm just going to flick through one more time and just see if I've not missed it. Check the website version. Just you can run it on the desktop, or you can run it to through a web browser. There we go. I think what I did wrong was I selected Python instead of Raspberry Pi. So on the Raspberry Pi specific version of Edublox, then Pimoroni has the Explorer Hat as one of the supported boards. So I can import the Explorer Hat library, and then I can say, make motor 1 go forwards. And if I want, I can now control the speed. So I can say go forwards at 25. I can say go forward at 100, that's full power, 100% power. We obviously want to have a pause in there. So I need to import the time library so that I can also do a time sleep for 1 second. Another second after I've set the speed, and of course at the end I also want to stop it by setting the power to 0. So if you look at the camera, when I run that, we should see that motor's running at half speed, then it sped up to full speed, and then it stopped. Now the really nice thing about Edublox is that we're in blocks mode, but I can click on here and see the Python code, and I can start to understand how to program this hardware in Python, and that full power of the Python language is something which I can then start to expand and learn. So you can start in blocks and then move on to Python, and it's a really nice way to kind of learn the language and the capabilities. If I switch back to blocks, you can see the Explorer hat has also got lots of other features I can play with. So I can turn on the yellow light, for example. So now when I run it, you can see next to the number 2, the yellow light's lit up. So I've got all of that ability to program my robot from Edublox, learn about how the Python code under the hood is actually doing that, and then I could take that Python code, put it into my Python editor, and write a more complicated robot. Once you start to get to grips with Python coding, you can start to interface your robots to more than just your code by adding other control mechanisms. And a very popular one is to use a remote controller for your robot. So the next robot I'm going to show you is going to work on exactly the same principles as the robots that we've just seen, but I've used Lego. So we've got a Lego chassis. It's got a motor on the back to drive the back wheels. It's also got a second type of motor on the front called a servo. Now, a servo is a special type of motor where you can program it through your code to move and stay at a fixed position. And if I send some code to that servo, you can see that the different positions I put the servo in actually control the steering of the front wheels. So I've got a different way of driving this robot. The back wheels are controlled from the motor, and the front wheels are steered with a servo. The rest of the robot, and we'll come to the controller in a second, is very much the same principles. We've got a battery providing us with some power. We've got a Raspberry Pi. In this case, it's one of the Raspberry Pi Zeros, the kind of really miniature ones. And on top of it, we've got a controller board. And this particular board is called the Picon Zero, and it enables me to drive motors through an H bridge, exactly the same as before, as we've seen on all the other boards. But it also has servo driving outputs so that I can make the steering servo work. The rest of the construction is just ordinary Lego. Now, you may be wondering, how do you interface your Lego to the Raspberry Pi? Well, we know a little bit about motors now. They have 2 wires, and if you connect them to the battery one way round, the motor goes forwards. If you connect them the other way round, the motor goes backwards. And all I've done is I've taken, these are the Lego Power Functions motors, and I've taken the 4-wire cable that comes from the motor, and I've chopped it. I actually took one of the extension cables so I could chop that in half, and the middle 2 wires the 4 wires are the 2 wires that go to your Lego. But I don't need those. I just need the middle 2 wires for the directly into the motor output for the H bridge. And I've only got 1 motor on this robot, so I only needed to use 1 of the 2 motor drivers, but I could have driven 2 motors off this. And then the other part, which makes this a really fun robot, is I've used one of these game controllers, and I will show you where to find the code for this robot before the end of this session, so that you can kind of download and use this code yourselves. So this robot, you can see, is a lot faster than the other robot, because I've used a nice powerful Lego motor. I've used some gears to actually drive it with a slightly faster gear ratio. But the other thing you might notice is that the more I push the stick, the faster it goes. So I've actually used the proportional control that the joystick gives me to tell the motor to go slowly, or if I push it all the way, to go faster. And in the same way, the other stick controls the steering. So the further across I push the stick, the tighter it turns the steering wheels. So I've actually got direct proportional control of my wheels and my motor. Now, of course, once you know the secret of building a robot is to have some motors to provide power and steering, you can build whatever motor powered robot you can imagine. So we could build a tank. Yeah, this is just a Lego chassis. It's got 2 motors on the back, which turn each of the 2 rubber bands to give them a bit more grip. There's a nice trick we found on the internet. And into the chassis, here's the wires, which are not connected to anything at the moment, but same principle applies. I've taken the middle 2 wires from the extension lead that I chopped in half. I've used 1/2 for each motor, and these go into the H bridge on the robot controller board, which sits on a Raspberry Pi, and we've got a robot controlled tank. I earlier showed you a 4-wheel drive robot based on a microbit. That kit was actually the tiny 4-wheel drive kit from Cortec Robotics. This is another robot using that same principle, but this time with tracks. So it's got 2 motors because it doesn't need 4 because the tracks drive the front and back wheel together. And again, one of the miniature Raspberry Pis plus the Picon 4 driver board. And in this one, I've also added a bunch of LEDs on a header extension so that I can attach 2 pieces of hardware at once. Now, how do I know that my 2 pieces of hardware are compatible? I use the website, which we looked at earlier. I'll just disconnect from my Raspberry Pi. The Pinout website. So I'm using a Pimoroni blinked, and I can see here that all it uses are the power, ground, and the data and clock pins. So just 4 pins. I'm also using a board, the Picon Zero by Fortronics. There it is, Picon Zero. I can see the Picon Zero uses pin 38 and it uses pins 2 and 3. So there's no overlap, which means I know it's safe to put both of these boards onto the same. I've just realized I wasn't sharing my screen properly for that section. I'll just quickly show you that again. So we're looking at Pinout XYZ, and I started off on boards and I looked for the Fortronics company. The Picon Zero is the board I'm using. And I can see that it's using pins BCM2 and BCM3. If I go to Pimoroni, who make the LED blinked, which I'm using, I can see that that doesn't use pins 2 and 3. It uses pins 23, 24, and that's it. So the two pieces of Raspberry Pi add-on hardware use different pins. Therefore, I know that I can put those on together and they're not going to interfere with each other. And this robot is using a Bluetooth PlayStation 3 controller. And I'll just wait the controller up again. I think because I've been talking for so long, the robot has shut down. So I'm going to reboot that one. While that's rebooting, let me show you a completely different type of robot. So we looked at servos on the previous Lego steering robot. If you look at my camera again, what you can see here is a robot arm, and this one is wired up to a game controller, which I'm going to just restart the code because, again, it's gone to sleep whilst I've had it set up in advance. So here I've got the ability to control this robot arm with this remote control. So completely different type of robot. Again, this is a kit which you can find in the suppliers, who will look at the links to the resources for. It's called the Me Arm. It's a build-it-yourself kit, and it has 4 of those servo motors controlling each of the degrees of freedom of movement. So really nice, neat alternative take on a robot kit. Now, once you've got the principles of robot building under your belt, you can go large. I'm going to show you just a couple more examples. Here's a robot tank. This is another kit that you can buy from the suppliers who I'll link to at the end. Again, principle's the same. It's got 2 motors, yeah, and you can see them inside there. 1 motor to drive each tank trek. But now you've got a much more powerful robot that can drive up better terrain and is more robust. But the principles are the same. You just need to pick an H-bridge board that is powerful enough for the motors that you run off the robot. So these smaller robots that we started looking at, like the STS Pi, this has tiny little motors, and pretty much any H-bridge will do. Once you get onto bigger motors, what you need to do is look up the specifications for that motor to find out how much current it needs. Current is like the rate that power flows through the circuit, and the higher current level that will be quoted will be the stall current, which is how much current do these motors take when they're static, when they're trying to turn but something's stopping them. And you need an H-bridge which is powerful enough for that rating, and then you won't damage your circuit by driving those motors. So nice big tank robot. You can use the same principle with your 4-wheel drive robot. So here's one using the Pi Borg, Monster Borg motors and some really chunky wheels. So now we've got a really fast robot, solid robot platform. But notice that the driver board on here, now I'm using one called a Thunderborg, and it can drive these much more powerful motors. So, but the coding principles are exactly the same. I could put the code to drive my H-bridges that I've used for all my other robots on this one and make the same control mechanism. And this one's now booted up and is ready to go. You can see it's got some nice green lights on, and this is a really nippy little robot. And if I just hold it still for a second, you can see that I've used the LEDs to kind of indicate the power level that I'm driving it at. So I'll show the joystick at the same time. And if you outgrow kit robots, once you've got the basic principles, you can start doing what I do for my hobby, which is you can start to design and build your own robots from scratch. So this is the competition robot that I built for the Pi Wars competition, and it is based on the Mars rover, Curiosity rover. So it has this rocker bogie suspension, which means that as one side of the robot is, it's difficult to fit it all in on the camera, as one side of the robot, let me switch to my other camera. There we go. So as one side of the suspension goes one way, the arm across the top rocks the other way. And it's a design that's intended for all 6 wheels to remain in contact with uneven terrain, which is what, of course, you wanted your Mars rover to do, because you couldn't go out to Mars and fix it. So you didn't want it to get stuck. And I built this robot designed from essentially all the parts were designed to be cut out of Perspex sheet using a laser cutter. It's got a nice touchscreen display so that I've got a really nice kind of menu on it. And you can see it looks a lot more sophisticated. But actually, how does it work? Well, it's got the same motors and the same wheels as you saw on the other robots. And the steering is done, they're kind of hidden inside the box here, but the servos, yeah, servos to turn the wheels. So the code is really the same principles applied to a much more complex robot. So we've seen a whole range of different robots, some examples of how to get started coding them. I'm just going to go back to the screen share to just share with you a few links, things that you will find useful. So let's just quickly recap on the electronics. So we were using this H-bridge type of circuit, and it enables us electronically to switch power to a motor to make it run forwards or to make it run backwards without having to connect and disconnect wires. It's also got one more neat trick, which I didn't show you earlier, and that is that if you close the switches on either side of the motor whilst disconnecting the battery, then you effectively lock the motor and stop it from turning, and it acts as a brake. So there's actually a third mode that you can use the H-bridge to, instead of let your robot just coast to a halt as it kind of drives along and slows down, you can actually kind of lock the wheels up by applying braking to the motors, by configuring your H-bridge to effectively connect both motors to the battery. So there's 3 places that you can find all of the kits and items which I've talked about. There's the Raspberry Pi store, the only one in the world, very convenient for us, is located in Cambridge. So you can go to the Lion Yard Shopping Centre in Cambridge and actually look at all of these robot kits, apart from the home designed robots. But you'll find most of what I've shown you today on the shelves in the Raspberry Pi store, and you'll get a ton of advice on getting started and what is right for you. There's a couple of companies which make a lot of Raspberry Pi equipment in the United Kingdom, and also import some of the Adafruit parts, which are one of the other companies that does an awful lot of educational robotics. There's Pi Moroni based in Sheffield. You can find them at pimoroni.com, and there's the Pi Hut, who are the other main UK supplier of Raspberry Pi and robotics equipment. I have no affiliation to any of these companies. They're just where I buy all the cool stuff to make my robots, and where you can buy stuff as well. And finally, I'll leave up on the screen the links to the different websites we've looked at. There's a couple I didn't show you, so let me just flick through them. There's the Raspberry Pi project site, where you will find a huge amount of projects on learning to code, getting started with the Raspberry Pi, Scratch and Python, how to build your own robots, websites. So tons of free resources on there, 3D modeling, and also details about code clubs and Coder Dojo, which are groups that you, once lockdown finishes, you can hopefully find in your area and go and meet. The other Raspberry Pi Jam is a public event where you can go along and see people's Raspberry Pi projects, get some training on coding. They're generally free to the public, and they're organised all over the country, in fact, all over the world. Another useful site to know about is the Magpie magazine. It's by the Raspberry Pi Foundation, and whilst you're stuck in lockdown, you might consider supporting them by subscribing to it, but they also make every edition available on their website to download for free. So you can download a free PDF copy of the latest magazine, and there's a ton of information in there. So we have 10 minutes of this session left. I've presented everything I had. So let's have a look at some of the questions in the chat, and I will try and answer what. So in the chat, I see how the chips are coded. So hopefully I've answered that question. by this stage, and also where to get the robots. If there are any other questions, if someone could put them into the chat window, then I will be able to answer. If not, then I hope you've enjoyed this session, and I will stay on the line until questions come in or until we get to the end of the hour. There's actually one more website I didn't show you, which I've linked to in at the bottom here, and that is where to get the code for the game controller. So I've published that code onto the GitHub website, which is a code sharing site. So there you can find instructions for how to install that code on your Raspberry Pi, and included so it supports a number of different controllers. The ones that you've seen you can buy from the suppliers which I mentioned, or you may already have a PlayStation 3 or a PlayStation 4 wireless controller at home. And there's a bunch of examples in that code library for the different robots. So for the Picon Zero board, I've got that Lego robot I showed you, a simple motor robot, and the Zumo Picon Zero robot. Someone's asked in the chat, can we have links to the kits? Yes, let me have a quick look. I'm just opening up a robot talk that I've done in the past, which answers that question. There we go. So there's the CamJam EduKit 3, which is probably the lowest cost robot kit you will find anywhere. There's the STS Pi, which is the slightly more sophisticated, shown here with the Raspberry Pi camera attached. So it doesn't come with the camera, but it comes with the attachment to put the camera on. There's the tiny four-wheel drive from Cortex Robotics. It doesn't come with the microbit attachment you see here. That's something I added on, but it comes with a Raspberry Pi controller board. The Microbit Robotics is the motor driver board for Microbit by Kitronic. It's upside down in the URL there, but you can see it's Kitronics. You'll find Kitronic's stuff sold by all of those suppliers who I showed you links to earlier. There's the home-built Lego robot if you want to do it yourself. And this chassis, which I showed you, the little mini tank, is called the Pololu Zumo chassis. And you can again find that from those Raspberry Pi suppliers. So those are the robot kits which I showed you. The one I didn't show you, so I haven't got a picture of here, is the Devastator tank. So that larger metal tank robot. This one. This one is sold by the Pi Hut. So if you go to their robotics section on their website, you'll find we can show you that on the screen share. And Maker Store Robotics. Maybe if I search for tank, we'll find it. There it is. Okay, any more questions? I think we're just about wrapping up. We're at the end of our time window. I think I've answered all the questions apart from, do I play Minecraft? Yes, I do play Minecraft. If you like coding in Minecraft, then Edublox, which I showed you earlier, has support for the Minecraft Pi interface, which lets you write Python code to control your Minecraft world. So that's a really nice way to get started there, because you can drag the blocks in to import the Minecraft libraries and very quickly get up and running. And yes, it says in the chat, which you might not be able to see, that if you have questions after the event, then you can email them to stemtastic@wsc.ac.uk, and they will forward them on to me, so we can get answers out to people via the Stemtastic organisers of today's activities. So I hope you've enjoyed this session and found it useful. I'm Dr. Footleg, and I hope you have an enjoyable robotics days ahead of you as you start building your own robots at home.